Untitled Chapter Institute, and before I introduce our fabulous speaker for today, let me tell you a little bit about the Institute. So, the Isaac Newton Institute is part of Cambridge University, but it's also the UK's main mathematics research institute. We run groundbreaking themed programmes on an incredibly wide range of topics, ranging from the maths of sea ice to the maths of forensic science, from big data to the maths of microbial communities, and from string theory to quantum theory. And of course, we also have the purest of the pure mathematics. All that matters is that it is groundbreaking research done by the best mathematicians from across the globe who are working in that field. One of the most famous moments in the history of the Institute was when Andrew Wiles announced his famous outline proof of Fermat's last theorem right here in this very room, on this very board. And in fact, this summer, as part of the Institute's 25th anniversary celebrations, both Andrew Wiles and his biographer Simon Singh are going to join us together to talk about that result. So the Institute is funded by the research councils, but we have ambitious expansion plans and lots of naming opportunities. So if anyone in the audience is inspired by what they hear today and wants to become a donor to the Institute, then do please get in touch with us. So you might have noticed that you were given a question on your way in asking about the amount of blackboard space in the Institute. So please put your answers, including your contact details, in the box. So there's one, or not in a box, it's a little tray like this, which will be on the table by the door on your way out, because the winner is going to get a Newton Institute mug. So obviously, I'm not going to tell you the answer, but I will just say that there aren't just blackboards in the seminar rooms, they're also in the lifts and even in the toilets. Now, on to our fabulous speaker for the day, Dr. Andrew Fitzgibbon. I could tell you that Andrew is a principal scientist at Microsoft Cambridge in their computer vision group. And I could tell you that he's an organiser of a programme on imaging and vision being held at the Institute later this year. I could tell you that he's published numerous highly cited papers and received many awards for his work, including 10 Best Paper Prizes at various conferences, the Silver Medal of the Royal Academy of Engineering, and the Roger Needham Award. He's a Fellow of the Royal Academy of Engineering and various other august bodies. I could tell you that I've known Andrew for almost 20 years now, since we were both researchers in Oxford, and that Andrew held a prestigious Royal Society University Research Fellowship there. But really, I want to tell you two things. First, not only is Andrew a brilliant computer scientist and mathematician, he also has won an Emmy for his work on 3D cameras and tracking. And also, that maths pervades every aspect of Andrew's life. In fact, recently he was renovating a house, and the tiles that they had were two different sizes of octagons. Rather than going with the usual configuration for these tiles, Andrew wrote a computer program to visualize all the different possible combinations. And having come up with the most aesthetically pleasing and shown it to his builder, he realizes that now they have what he believes is a brand new tessellation. It's important to me that Science Festival talks show you not just that maths is useful, but also that it's cool, that it's fun, and that it's beautiful. And I cannot think of anyone better able to do all of that than Andrew. So it gives me great pleasure to introduce you all to Dr. Andrew Fitzgibbon.
Thank you very much. That's the most overwhelming introduction I've ever been given. Welcome. It's fantastic to see you all here. I used to be nervous when giving talks, but I've been doing it for 20 years, so now I'm relaxed until today. I'm going to talk about a few things. One of the things I'm going to talk about is something quite new. It's this device here, which is called the Microsoft HoloLens. Has anyone heard of this? Okay, so a few people, maybe 20% of people have heard of this device, so I'll explain to you what it does. There's a picture of it up here. I'll explain to you what it does, and then I will sort of go back in time and show how what it does is similar to putting special effects into movies like Lord of the Rings. And I want to try and give you a picture of the mathematics involved in all these activities, special effects and the HoloLens. So, and there's I put a little asterisk on holograms to remind me to apologize. If you know what a hologram is, this is a new type of hologram, right? What is a hologram? It's a whole thing sent, redepicted hologram. So there aren't any lasers. It's not a hologram in the Gabor sense, but we'll just all have to get over it. Did you know that the word email has a proper meaning, and it's to bang patterns into a piece of metal? It's just that nowadays we use it for another sense. So the words may change. That's what I'm going to say. There will be videos of cameras moving through the environment. So if you watch one and you don't like the look at it, just look down at the floor and get your neighbor to nudge you when it's done. Most people have no problem, but I'm just letting you know that some of the videos involve a slightly wobbly percept. I'll tell you a little bit about me and my journey to where I am. I grew up in Cork in Ireland, and I went to university in Cork where I did maths and computer science. I had a fantastic summer job when I was there, which was being a water taxi driver, which was great fun because most of the day nothing happened. So I just sat in the boat and read books and played with mathematics. I went to Edinburgh after I did undergraduate. I went to Edinburgh to do a PhD, and I devoted an awful lot of time to studying the geometry of the ellipse, a simple shape, more complicated than a circle and a line, but easy enough for me to think about. I moved to Oxford University, where I looked at, instead of 2D shapes, I started looking at 3D shapes. But the shapes of things that I looked at were rigid objects that didn't move, so things like statues or the world around us, minus the people. And then I moved to Microsoft, and my research at the moment is trying to do the same sort of thing, which is sort of look at 2D images and figure out what 3D shapes might be, but of objects that are very hard to keep still. It's quite hard for this dolphin to hold his pose for long enough for a camera to spin around him. So that's a subject that I'm looking at the moment. So what is this HoloLens? Well, a HoloLens is a device you wear, and inside the device, up here, there are two screens that come in front of your eyes. And when you wear the device, so if you look, this woman is in a sort of an empty kitchen. It's got a radiator and it's got a hob, but the walls are empty. When you wear the device, it superimposes on the real world, which is what we see here, computer graphics. So a rendering, a depiction of some virtual world. And this is called augmented or mixed reality. So there's the real world, and here's the augmented world. And why is it useful? It's useful because, for example, in this case, the person wants to buy a new kitchen or get a new fridge. So we can display information about the choices that are available on top of the real world. The world in which she is moving looks a bit like this. So she's going to put on the device. And now this represents the virtual world on which she has a little viewpoint. The most difficult thing about this is that the virtual world must stay still. So here's an example where students are looking at a human brain. This student is far away, looking at it from her bedroom. We have another remote viewer here. And all the time, these 3D graphics must not move. And I'll explain to you how difficult it is for them not to move. This person is augmenting a real model with computer graphics. And I hope you can see that the potential applications go on for a long way. Now, this audience, I understand, has younger people in it. So one of the applications that I thought was fun to talk about was this one. So this is a video where Lydia here works for Mojang, which is now part of Microsoft, works for Minecraft, and they're going to show you how the HoloLens might be used to play Minecraft. You can't do this yet, and it's really, really expensive. So don't get too excited, but think about the future.
You can play the Minecraft you know today on HoloLens. Zach grabbed his Xbox controller to play through a giant holographic portal into a 3D Minecraft world right on the wall. Even though I don't have a HoloLens, I'm able to play together with Zach from my Surface.
Are you gonna come join my game, Lydia?
I'm in now.
I see you, jumping around.
One of the cool things about HoloLens is that it lets you display Minecraft virtually anywhere. You can get different perspectives on your Minecraft world. It's awesome to play with the controller, but could we show them something new, Sax?
Sure. Just take our experience off the wall and then put it on the table over here. Create world.
So if I pause this for a second, you saw the other camera person with a huge camera rig. So that camera rig is trying to show you what Zach sees through his HoloLens. So this is a real table, and in his device is getting superimposed this virtual world. So he can only see a little corner of it, but we can have an idea of what he's seeing.
As I run around the place, Zach can easily navigate and manipulate the world using his voice and his hands. He can walk around the hologram, pan around for different viewpoints, and even look inside.
So this goes on for a long time. It's very exciting. They discover an underground cavern, etc. You know, if we have time at the end, you can come up and watch it. Okay, so what is this device? Why am I so excited about it? So it's a device, as I say, here's a picture of it, which contains a computer. Everything in it is self-contained. It doesn't work with reference to any external devices. So inside here, there's a powerful computer, and as you can see from this exploded view, there are a large number of what can only be cameras. Okay, so if I look here, 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 we see all sorts of things that are cameras. What does the device use the cameras for? It's not for taking pictures in the sense that you would think. It uses the cameras to understand the world around it so that it can place the 3D objects into that world. I'm going to try and show you how it does that. That was one picture of what's inside HoloLens. The other thing that's inside HoloLens is science, engineering, incredible design, and a lot of mathematics. And those, as much as that hardware, are what makes it work. I want to talk a little bit about mathematics. Who loves maths? Good, good. That's a decent number. Last time I asked that, it was in a room of 8-year-olds, and all the hands went up. So, you know, let's go for more hands. Christy mentioned this. Who loves poetry? Fewer. I think all the hands should be up for both questions. I want to expand on something Christy said at the start. We think we study poetry because it's beautiful. We never think, oh, I'm studying poetry because it's useful. But poetry is useful. Poetry helps you to understand that you shouldn't end a sentence on an unstressed syllable. Poetry helps you to keep a rhythm as you speak and as you argue. If you want to make lots of money in the world, one of the things you have to do is go and make a pitch to venture capitalists, ask people for money. And if you understand how language works and the rhythm of language, you'll probably do a better job. You'll probably make more money if you're good at poetry. But that's not why we study it. We don't study it because it's useful to make more money. Almost all of my lecture is going to argue that mathematics is useful. And yet, that's not the reason I want you to love it. Right? I want you to love it because it's beautiful. And that's just, I hope we can see that as we go through. Now, it occurred to me that I'm supposed to give this lecture. There's lots of maths in it, fairly advanced maths at some stage. And the audience could be, I don't know, who's the youngest? Is anyone under 10? Yeah, a few people under 10. I I don't want to find out who's the oldest. If anyone wants to volunteer being over 70, feel free, but don't feel you have to. Excellent. And so if you're under 10, you've only seen a little bit of maths so far, right? And you don't know what's coming next. I remember when I was about 10, I thought that what was going to happen next was we were going to multiply bigger and bigger numbers, right? Or we were going to do longer and longer division. That's what I thought was coming up in the future. And even when I finished school, I didn't really understand what was going to happen next in maths. So that's why this slide is called All of Maths. You know, we've got a few minutes, so I think I can teach you all of maths in a few minutes. And of course, if you're older, if you're very much older, you probably knew all of maths once, but you might have forgotten it. So again, this slide will be helpful because you'll be able to get it all back. So what's the first thing you do when you're learning maths? The first thing you do when you're learning maths, you learn counting things. Look, there are 3 shapes here. And you learn about shapes, the names of shapes like circles and squares and triangles. And you might know about things being bigger than things or things being smaller than things. I don't know if you get this sign meaning less than when you're under 10. Do you get this sign less than under 10? Yep, good. Yep, good. And you learn simple sums, like adding. And fairly quickly, you learn that you can do fun problems. Right? So you can do fun problems like, what is the missing number here that gives me 7? It's 4. Excellent. You can do even more fun problems. Right? You can find the missing number that gives me 12. Hint, it's 4. And basically, that's all of maths, right? But I'm going to expand a little bit. Some funny things happen. So somebody says to you, what's the missing number here? What's the missing number here? -1. You invented a whole new concept because you had to solve this equation that didn't fit the earlier thing you knew. If you didn't know about -1, you'd be a bit stumped when this arrived. Then later on, and again, I don't know what age this happens, but instead of using boxes, we use letters, right? So this is exactly the same problem as we had over here. It's just that we put a little letter saying, what is X? And it's funny because small changes in maths can make things look very complicated. So I don't think anybody in the room was scared by 3 plus box equals 7. But sometimes it looks a little bit more sophisticated when there's X's there, and you might think, ooh, that's harder. But it's the same problem. And we call that algebra, or it's an idea of what algebra might be. The other great thing that maths has in it is pictures. So you might have pictures of coordinate systems. This is really useful. So X and Y axes. This is really useful when you're drawing graphics on a computer because you can make things move around the screen, which has 2 dimensions, X and Y. And at some stage you learn about graphs, right? So this is a graph of how hungry one is. When one wakes up in the morning, has breakfast, comes up to lunchtime quite hungry, has some lunch, less hungry, up to dinner time, etc. So a graph is a useful way to express ideas. So that's great. I'm not sure what age we are now. What are we? About 14, maybe 12, some age like that. You also learn things like you go back to shape. So here we had triangles and squares, and we look at triangles again, but we talk about more interesting things and more complicated things about triangles. In the triangle, there are 3 angles. Angles have things like cosine and sine on them, and we call this trigonometry. And this is sometimes the point at which we teachers try and tell you this is going to be useful one day. Right? If you ever need to design a garden, which is 3 exact angles, we will tell you, you need to know this rule. And you all know that's not true, right? You all know you're not going to do it. No one is going to, write a program to design the tiles for their house using trigonometry. That would be insane. And I'm telling you, that's not what it's good for, right? It's good because it's like poetry. It's something exciting. Look, we're nearly halfway through all of maths, so that's good. Then something funny happens. Right? So something funny happens because I had 3 plus box equals 7, and now I've got box plus box equals 3. I'm going to finish this up here. So now it looks a bit complicated. Right? How do I do box plus box equals 3? Any guesses? 1 plus 2. That's a good one. Any other guesses?
Divide 3 by 2.
Divide 3 by 2. Is that what you mean?
It's 2 boxes.
Oh, I see. Okay, so can I say 1.5 plus 1.5? Yeah. 2 plus 1, exactly, which I'm going to say is different from 1 plus 2.
7 add minus 14.
7 add minus 4, excellent. Now I'm going to do something with those numbers. For each of these numbers, I'm going to go out that much, right? So that's out 1, up 2, and put a dot. And now I'm going to go out 1.5, up 1.5, and put a dot. Out 2, up 1, put a dot. Out 7, up minus 4, put a dot. And what you can see is that there's an infinite number of dots which fit these 2 boxes. So what's happened? What's happened is, and of course I just call my boxes X and Y because, you know, we like numbers, not boxes. So what's happened is, algebra, mathematics, a problem, sum of boxes equals 3, turns into a picture. This equation relating numbers, or letters and numbers, is actually a picture of a line. Look, here are all the answers to the equation. It's a line. And this is a sort of a big tool of mathematics. I might claim this is one of the biggest tools of mathematics. I can turn pictures into numbers. I can do more complicated pictures. This little 2 above the x means x multiplied by x. So it's a multiplication and a sum, and that draws a picture of a circle. I can be even more complicated. I can say, what if I solve both of these equations at the same time? And what I've got is something called simultaneous equations, nasty nonlinear simultaneous equations, and that tells me the points which are on both the circle and the line. So that would be this point here and this point here. Right, 3/4 of the way through all of mathematics. Other stuff happens on the side. Right, so you could do all the mathematics without ever knowing what a vector is, or a lot of mathematics without ever knowing what a vector is. What is it? It's a list of numbers. Or what a matrix is. What's a matrix? It's a little square table of numbers. Vectors and matrices are handy ways to deal with shapes and geometry. You will learn by far the best thing in mathematics. Who knows calculus? Who has heard of the word? Almost everybody. And who's done any of it yet? Right, roughly half, and you're all on this side. Interesting how you arrange that. What does calculus do? It lets you do things that sound really boring, like compute the area, or find the lowest and highest points on a curve. But this is the tool that I probably use most often. I probably use calculus every day. It's great. You really, you know, it's going to be great. Think about these things when you... And then finally, we might talk about things like 3D shapes. How do we describe a sphere? How do we describe a saddle? And then something cool happens in mathematics. This is now kind of getting towards, you know, end of school, university. It all becomes incredibly simple again. Suddenly you talk about sets, which you've probably done in primary school, and then objects, which sound simple, like groups, sets of numbers or sets of objects. And a lot of what you do in advanced mathematics involves operations like plus. But this mathematics, the more abstract mathematics, is where, in a sense, all the exciting stuff happens today. So we've gone full circle, but all the time I'm going to claim we're talking about shape, and we're talking about linking shape to letters or algebra or equations. Good. Now you all know maths, so we can proceed. Okay, let me talk a little bit about special effects. Here is a frame from the first, I think the first movie that my software was ever used in, the first sort of publicly released movie. This is, you can imagine it's some war film, and this is just one frame of the 140,000 that appeared, that were displayed to you one after another at 24 frames a second if you went to the cinema to watch this film. And as you know, even 16 years ago, you know, films had a lot of special effects in them. But I think even today it's surprising to know that this is the frame you saw in the cinema, and this is the frame that was captured by the camera. Okay, so somebody, you know, went to a lot of effort, got some lots of people, trucks, fire, explosions onto this remote quarry in Russia. You know, they got the cameras there. It's really expensive and difficult. This is what they filmed. And then they painted almost everything in afterwards. So I'm just going to flick again. You might not even believe me. If you look at this sort of construction here. Oops, I think you'll agree that it's the same film. You'll notice that there's water up here. There are ships with their with their smoke blowing the correct way, because people don't make that mistake anymore. There are trucks here zooming towards the action. And again, so what I'm saying is there's a huge difference between what's captured and what's displayed. And every time, this is 140,000 frames, every time the camera moves, you have to update, you have to fix the image to stick all this graphics on top of it. Here's another one that I worked on. So there's a sequence here with some boats. Oh.
They're coming for me.
This is from the trailer. Okay, so thousands and thousands of boats. Yes, wooden boats, and I won't say anything about the acting. If anyone here is involved in the Greek play or such things, does things in Greek, it would be a great favour to me if you could overdub this whole thing in Greek and then subtitle it in English, and then I could really enjoy it, because it wouldn't feel so wooden. The dialogue wouldn't feel so wooden if I were reading it. That's just a project for anyone. Subtitle Troy, overdub Troy in Greek. So you saw thousands and thousands of boats. This is the raw footage that we were given to work on. Not as many boats. Those green dots are not in the water. They're not buoys in the water. They're dots that we put in afterwards to set up a 3D world in which we could put the computer-generated boats. So we did some mathematics in order to plot these dots, and what you should believe if you look at this picture, we'll see this many more times, so what you should believe when you look at this picture is that those dots are somehow stuck in the water. Obviously the boat is going past them. But that the dots are behaving as if they were stuck to the real world. And I'm going to claim that that's very complicated, and show you how to do it. Here's a simpler example that I'll use. This was one of the very first sequences we tried out this technology on. I presume you can spot the virtual object in this sequence. We haven't gone to a lot of effort to disguise what's happened. So, how do I stick the virtual object on top of the video? Well, it turns out it's actually very hard to do it just by positioning it manually frame to frame. It's just, it jumps around quite a bit because the camera is handheld. So what are we going to do? Well, what were we given to begin with? Here's the same sequence without the virtual object. This is what I'm going to feed into my program, into my analysis. Now, that is very, very complicated. If we think of that as a sort of mathematical object, look, there's, I don't know, let's say it's a long time ago, so let's say there's 1 million pixels with 3 colors, red, green, and blue at every pixel, so let's say that's 3 million numbers. And those 3 million numbers, in a typical shot, we might have 100 or 1,000 frames, so maybe we have 3 billion numbers. And those 3 billion numbers represent very complicated things like lighting and stone and glass and all sorts of complicated stuff. How are we going to turn this into something mathematical that we can understand or we can deal with? Well, there's a clue from 1970s, something called the Johansen dots. So this person is rolling a wheel with 2 lights on it. We turn off the lights in the room and we video it. And now we've only got 2 points. You can imagine 4 numbers, x, y, and x, y, describing what happened in that scene. And yet those 2 numbers, those 4 numbers, give us some idea that maybe there was something rotating. So let's try it again. Here's another object with dots on it. You can have a bunch of guesses as to what that object is. But when you play the video, I think it's quite clear that it's a dinosaur eating a lion. What are these dots? You might guess now, but let's have a look and see if it becomes clearer. And again, I believe you all know or have a strong feeling for what was happening there. Here's another one. I won't try and demonstrate this one. Even there we saw who was in front of whom. So I think I'm trying to persuade you that I can take the huge complexity of the world and convert it into something smaller. So now we're using even fewer dots. We only got the top half of one person and the bottom half of the other. Who has seen this before? I'm so happy. So these are called Johansson dots, and you can find other instances of them on other objects. So what I'm trying to persuade you is that the world is rich and complicated, and what did I say? 3 million numbers per image times 1,000 images, 3 billion numbers. But maybe if we can find a way, we can turn it into just simple geometry. Just a small number of x, y points in the image. Okay, so what's this? What's going on here? Guesses? Yeah.
Basically, when you put the video on a computer, it creates thousands of dots, and then it scatters it all around the picture.
Pretty close. So I'll just play that again. So I think you might have the perception that someone is moving maybe through an environment with a camera, turning around a corner. And this time, instead of, kind of as you said, instead of sticking dots onto the world, we just took an ordinary video. So this is the video from which, and we just applied a very simple piece of computer algorithm to the video, which basically looks for interesting corners. Looks for little tiny dots, areas on the video that are different from the area nearby. This is longer than the original. And that gives us this cloud of dots. So we maybe have some idea how we're going to solve this problem. Now, I haven't even told you what the problem is yet. The problem is this. In order to stick a special effect on a video, it is very useful, in fact it's sufficient, to know the path that the camera took through the world. And you might think, oh well, that's easy, just put a GPS on the camera. But GPS, A, is extremely inaccurate. We need to be sort of centimeter accurate here. And B, GPS doesn't tell you anything about the direction in which the camera is looking. And a compass is too inaccurate. The only thing we can use to tell us what the camera is doing is look at the video. And what I'm showing here is the result of an algorithm that I'm going to tell you about, which looked at the video and decided that each one of those bright dots is one of these red dots. It's like a plan view of the world. And the blue path is what the camera person, the path that the camera person followed as they went through the video. I just drew these black lines in to give you an idea of what the shape of the room is. So what I'm going to do is try and figure out how do I go from a set of two-dimensional points, the clouds of dots, into a three-dimensional picture. And to do that, I'm going to show you the sequence we originally looked at running in the program that we wrote called Boujou. It was going to be called Imogen, but it was rude in some language that I can't remember. So we had a morning to think of a new name, which was Boujou, which is from the French bouger to move, and bijou meaning a jewel, so a sort of a beautiful moving thing. And while I chatted, the program was looking at every individual picture in the video, so you can see it moving slowly through the video, finding those bright dots, except now I'm just coloring them with a red X. And every time it moves to a new frame in the video, it connects each dot with a yellow line to the most similar dot in the previous frame. So we end up with this, what I call a set of trajectories or tracks. So each one of these yellow pathways represents some point out in the world. There's a point out in the 3D world at the edge of the curve, which the system has automatically decided was a 3D point moving through the environment. But now I've got a long set of two-dimensional information. I want to convert it into 3D. I'm going to tell you later how to do it. For the moment, let's just watch the computer have a little think. And now it's converted each of those tracks or trajectories into a 3D point. Ignore the difference between blue and yellow for the moment. And we can have a look at what it thinks happened there. So what it thinks happened, and you'll notice that we have a very sparse, it's not a very rich 3D model of the world. What's happened there is we've got yellow and blue dots, and also a hypothesis as to what the camera was doing. So this red path here, and this picture of what the camera saw, is moving through the world in the way that it did. And it figured all of that out just by looking at the video. Now what the person is going to do is going to select, so, I said it's a very coarse 3D model, but maybe you would believe me that this square here is like a planned view of the building that was far away, which is going to have the ladybird on it. And maybe you might believe that this set of yellow dots here is the wall that was to our right as we walk through the scene. So what the user is going to do is select these dots and attach to those dots, here's a close-up. Attach to those dots the ladybird, say, stick the base of the ladybird onto that collection of dots. And now we play it through, and it looks as if the ladybird is attached to the scene. How did it get there? It got there because I figured out what the 3D geometry was, what the 3D structure of the scene was, by looking only at 2D pictures. And this is slightly different from how your eyes work, because you have two eyes, or 90% of people have two eyes which tell them what happens in 3D. This is the kind of perception you'd get if you closed one eye and walked through the world. You still get an idea of what's happening in 3D. One more thing I want to show you just is exactly how much the ladybird jumps around. So the way we make the video in the end is I generate this black and blue video with the ladybird in it, and then I stick that on top of the original video. If you see how much the ladybird jumps around when the background's not there, and how stable it looks when the background is there, it looks stable because, of course, your eyes are adjusting to the background. You're compensating for the motion. But this explains how difficult it would be for an animator, for someone to just manually position the ladybird in every frame. Okay, so that's fine. So how do we stick computer graphics in the real world? We find out 3D geometry and we find out camera motion. Let me tell you a little bit about the maths that's involved. The basic maths that's involved is something called a pinhole camera. So a mathematical model of how cameras work. Has anyone built a pinhole camera? Good, good. More of you should. That was maybe 20% again. It's a lot of fun. What happens in a pinhole camera? It's an amazingly simple object. It's a box with a tiny hole here and a piece of tracing paper or greaseproof paper here. And it looks at the world, it forms an image of the world on the back of the box. Here's a diagram of what happens in a pinhole camera. Objects out here in the world get turned, as you all know. They come upside down on the screen at the back. That's okay, the computer can cope with that. So objects get, 3D objects in the world get turned into a two-dimensional picture on the background here. What's the key thing about the two-dimensional picture? Well, it's the laws of perspective. What is perspective? Perspective is a way of, you can think of it as, from the Renaissance, you can think of it as a way of making art where a 2D picture looks like it's from the real world. And art is a great way to explain perspective, and there's a particular piece of art from an Irish artist that I like to show that I think explains it quite well.
are small, but the ones out there are far away. Small, far away. Get it?
So I think what Ted is trying to explain to Dougal here is something called similar triangles. So if we have a picture of an upside down rose in the camera, it could be a small rose nearby, or it could be a large rose far away. So I'm going to turn this into mathematics. So how am I going to turn it into mathematics? I'm going to introduce some letters, some variables. So I'm going to say, there are two things I don't know here. I don't know the height of the object. Imagine that I'd never seen a rose before. I don't know the height of the object, and I don't know the distance from the camera pinhole to the object. And I'm going to call that Z, and I'm going to call this Y. So Z gets bigger as you go far away. Y gets smaller as you get small. So when I see a picture of something in the image, there are two things I don't know: the distance and the height. But there's a rule I can use from geometry, which says that the height in the image divided by the distance to the pinhole, called the focal length, must always be the same as the height in the world divided by the distance Z. So here I've got an equation. Now there's two things I don't know here, right? I do know the height in the image. I can just look at the picture and measure that. I do know the focal length because I built the camera. So I know this stuff, but I don't know either Y and Z. I can play around with this equation. I can say, well, there's the height in the image. It's known focal length. Whatever goes on, I don't know both of these things. And I'm going to say, this brings us back to the kind of problem we had here, right? Where there are two things I don't know, but yet I can still say something about what happened. Now, in this case, it's going to be more like a multiply. I know it's a divide, but I'm going to pretend it's a multiply. I'm going to make you do this little problem. What goes in here? 2 times 3. 1 and 6. Etc., etc., right? 6 and 1 is good. 12 and a half. So again, I have an equation with lots and lots of different answers. In fact, here it turns out that the geometric picture is something like that. Anyone shout if they think that's wrong? But something like that. So I don't know both of these things, but I've got some handle, I've got some clue as to what they're going to be. Now it turns out that, in fact, that was a one-dimensional picture, like a side view. There's actually a two-dimensional picture. Here's my image again. Here's the tracing paper at the back of the pinhole camera. In fact, I have two equations, x and y, for a 3D point, x, y, and z. And I don't know, I know x and y, I know f, but I don't know these three things. I've got two equations, three unknowns. I still can't solve it. But what I can do, remember I mentioned matrices and vectors, is rewrite my problem in terms of a matrix and a vector. Now, at this stage, you'll see. Okay, so let's go back to my office scene. Here is one of the tracks. So I want you to park the idea. Matrices and vectors are going to be useful here. Now let's see how they're going to be useful. So back to my office scene. Here's one of those points that I track through the scene. I look at frame 1. I just write down the distance from here to here and the distance from here to here. That's x and y. Stick them in a list. Move later on in the scene, do the same thing, write some new numbers, x and y coordinate. And then sometime it disappears from the video, so I just put like no value in my list. So this one 3D point in the world became a long list of numbers, typically 200, 300 long. Another point becomes another long list of numbers. I keep doing that, and I get this huge table of numbers. So where there's white, there was a number, and where there's black, I couldn't see the thing. And just like my 6 equals 2 times 3 example here, I know that this huge long list of numbers is basically a small set of numbers, which are the camera positions, and another small set of numbers B, which are the 3D points.
Now, at this stage, I'm just going too fast, right? But the point is that the same job you did in thinking of factors of 6, you can think of ways in which the scene could be understood. And just the same ways you couldn't uniquely discern which factor was which, it turns out that you can do all of this work and you'll never know how big the scene is. So looking with one camera, you can't tell the difference between being in a small model of this room or being in this room. That's the ambiguity that's left. And then I want to show you one big equation, and then we'll be pretty much stopped. What I want to show you here is the way I write down the mathematical problem that we have to solve. What I want to show you is that there aren't very many characters in it, right? There are all sorts of new symbols. Look, this dot with a circle on it is a funny way of multiplying matrices. If you know matrices, there's already a funny way of multiplying them. This is even funnier. There are lots and lots of bits and pieces lying around here with vectors and matrices. But really, this problem doesn't have many letters in it. It's not very hard. It's harder, it's harder to state than the classic problems, but it's an easily stated problem, and we have no good solution. Here at Cambridge, I have a PhD student who is making amazing progress on solving this problem, but yet there's no good solution. However, I just told you that we have this program Buju, which can do it for special effects, and I told you we have this device, the HoloLens, which does it in real time, all the time. And how do we do that? Well, we do engineering. We make approximations. We learn from physics and mathematics, and we find solutions that work well enough in practice. That's all I'm going to say. So, 10 minutes. What's going to happen next? Well, the things I'm interested in the moment. So you notice that we figured out the 3D world, and we figured out the movement of the camera in the world. But really, in that video, in all of those videos, nothing was moving. Yes, the sea was moving, but it turns out it's easy to deal with that. Yes, there were cyclists moving through the environment. Yes, there was somebody playing at their computer. But the bulk of what we were looking at was a static world with no moving objects in it. If we look at a video like this, essentially the interesting object, the object that we want to care about, is this dynamic jumping object, and I would somehow like to recover the 3D shape of it. Now I know from this picture it looks like I have recovered the 3D shape of it. That's because what I'm doing here is taking a generic model of a four-legged object and asking the computer to fit that to describe the video in those terms. The thing I'm working on at the moment, or my project for the last 5-6 years, I guess, has been to try and look at whatever is happening here. So what do I mean by whatever is happening here? There's some class of object here. You know what it is because you're a human, right? You know what dolphins are, but imagine you've never known anything about this shape. And what I want to do is have the computer figure out what shape are dolphins. And what it's going to show by figuring it out is by looking at those images, it will produce this program, which allows me to generate all the different shapes of dolphin that you can have, just from looking at a small set of images of different dolphins in different poses. And the way it does that is by making a hypothesis of a 3D model that could explain the images, and then kind of at the same time learning these sliders so that it fits the images. Why do I do this? It's not because it's useful, right? I can say, oh, it would be really useful if you had a new picture, then you could pop out a 3D model and maybe you could paint on the 3D model. And that's true, right? We would love it if we could do this. But really we did it because it was hard, right? Because we had solved the case where the things weren't moving, and now we want to solve the case where the things are moving. And why dolphins? Because they were easy enough to do and hard enough to be hard, if you see what I mean. So we tried it on polar bears, didn't work. Tried it on pigeons, worked very nicely. And this is how our research proceeds. So once I can figure out how to do polar bears, I'll try to do pairs of polar bears or mice or something. In fact, I have another PhD student looking at this problem. Very good. That's where I am. Thank you.
Thank you, Andrew, for what was a just fabulous talk. I'm sure that there will be lots of questions. Would anyone like to start off with a question?
I have one.
Candy, yes.
How do you animate hair?
Ah, good one. Really hard. Really hard. Best way at the moment, because computers are really powerful now, is pretty much one in each individual strand.
At a time.
At a time. So hundreds of thousands of strands all in the computer. And you can't do them one at a time because they all touch each other. So you have to do it all together. It's a huge problem. And we still don't have a good, I mean, there's not much good hair in computer graphics movies. My favorite hair, I think, is, Sully in Monsters, Inc., which is kind of fake hair, but that works really well. But yeah, it's totally a problem, and we also don't know how to, some of my colleagues are looking at how to just take a real person's hair and kind of extract that into the computer, but that's really complicated as well. On the list of, too hard for me at the moment.
Yes, it's black.
Are you applying your technology to driverless cars, or?
I'm not. I'm really excited by driverless cars. I think nothing is going to change the planet more. But I haven't got around to doing anything to it. Yeah. Yep.
Could this technology aid video conferencing and so on, where you could boil the face down to a set of equations, transmit that, and then repatch that together?
Yes, we continually have this. It seems like that would be great, because then you get a much better resolution model at the far end. But have you heard of this term, the uncanny valley? It's when you try and take a computer graphics face, and if you make it look like Sully from Monsters, Inc., everyone's happy, looks real. If you try and make it look like me, it just looks spooky, even spookier than normal. And every time we try this, teleconference thing, you fall right into the uncanny valley, and you're better off with low quality video than a high quality, nice 3D model. But one day,
Yes.
Do you think that this deep neural networks which figure out something about the objects, do they somehow actually use the same algorithm somehow inside? What do you think?
Let me explain deep neural networks. So what do neural networks do? Neural networks do this. Here are some examples of something. And what neural networks do is give you a way of filling in the values in between. Right? So if this was, I don't know, weight and height, and you wanted to say, is this a likely weight and height? So what do neural networks do? They turn a list of numbers, a bit like my big matrix, into a smooth mathematical object, something that you can do stuff with. So, for example, in my dolphins, I have to take numbers from the computer and generate a smooth mathematical object. You can do that with deep neural networks, or you can do that with a bunch of other technologies. But deep neural networks are exciting because they seem to be able to do this, guessing what's in between, better than anything else we've met so far. And we don't really know why.
And do you use supercomputers in doing fast animation?
People do. When we're working on the HoloLens, we are limited by, there's no fan, and by what you can carry on your head. So for me, I really love making making the fastest possible code on the device you have. Whereas with supercomputers, there is a tendency to just buy more supercomputers.
Augmented reality applications I've seen, including the HoloLens, don't seem to take account the lighting from the environment. So how mature is this technology for consumer applications?
Oh, well, for consumer, I would say, we're not really, at the moment we're looking at what you call it, business applications, or, so somebody is maybe, trying to fix an elevator shaft or something. And there, what really matters is that you've got a display which you can put over here, or I was talking to a surgeon recently. So surgeons, have to look at the image of the thing they're looking at and the actual person. So it really doesn't matter that it's like Princess Leia, pale blue rendering. I mean, it's a full color rendering, but it definitely, you can see the world through the background. It doesn't matter what's good, is that I'm working here and I can just look over there and see this, computer data. The other great thing about augmented reality rather than virtual reality is that most of what you see is the real world. So number one, you're much less likely to have any sort of motion sickness because most of your visual field is full of real stuff. And also it's very easy to just put it on. You don't have to switch into one world or another, and of course you don't bump into things, which is good. So I think if your goal is to have a fully realistic virtual world, then augmented reality would not be the way to do it. But if your goal is to do something useful with bits of imagery near you and safely, then I must admit, when we started this project, I thought it was a bad idea because augmented reality is much, much more difficult than virtual reality. So the engineering was just terrifying. And I must say, I didn't do the code that runs on it. Some very clever colleagues did that. But now that it works, I'm really delighted because I think the fact that you can see the real world is really valuable. You were asking. You've been asking for a while. Yeah.
You mentioned when it was capturing the image of the street, and the camera was walking through the street and capturing the image, and you said the computer was choosing interesting points. Why did it ignore the bicycle rider?
It chooses interesting points, and then it checks that it takes the largest number of points that are moving rigidly. Mm-hmm. Right? So there were a few steps that I didn't tell you about, but even when it's just doing frame to frame, i.e., matching two frames, so it says, lots and lots of potential matches. And if you think about the railings, maybe you recognize there were some railings in the background. Each one of those looks like each other, so there's all sorts of wrong matching from railing to railing. But because it asks for the single interpretation that's rigid, it throws all the bad stuff out. Great question.
Is it easy to add shadows on augmented reality?
It is certainly easy to do the computer graphics. That we know how to do shadows in games. And some augmented reality devices have sort of dimmers, so you can cut out the real world. And then what you would do is darken the bit of the real world that you needed to do. The HoloLens doesn't have a dimmer, but in the future devices may have dimmers. One more and then I'll take it.
Yeah, sure.
So, speaking of the future, if you move forward and you can actually create a wider view of actual reality in a lens, then could that be used to help blind people? So that would connect to their brains, so that brain would interpret whatever the reaction to the real reality is.
Yeah, there's, so obviously you wouldn't have the displays, but there's all the other sensing in the device. And yes, some of my colleagues are looking at that. It's really interesting how to do it. I mean, obviously, if you could feed directly into people's brains, that'd be brilliant. But even before we're able to do that, because that looks like it's a long way away, might it be useful to be able to talk to somebody or to make a sort of, So the other thing the HoloLens has is spatialized audio, which means it can make things sound like they're coming from behind you or in front of you. So something else people are wondering about is, could I have like a little ping where the door is? Or maybe if there's an obstacle that I don't want to touch, I could make it make noise. So yeah, we're interested in that. There's one more, I think. Yeah.
It occurs that this technology could be used to save lives by preventing people entering dangerous environments by scanning and so on, and then being able to capture that and engineer the environment without actually having to put a person in there.
Yes, I mean it's always going to be a worn technology, but absolutely one of the things it can do is show you information behind walls, inside some. So, for example, if you're an electrician, an idea is that it would show you the existing wiring, or maybe not an electrician, or somebody who's making a hole in a wall that would show you the existing wiring, and that would stop you hurting yourself. If you're a firefighter, I mean, these are all, I'm making this up as I go along, but if you're a firefighter, you could do somebody outside the building could be pinpointing where you should be going, and then that would transmit to your device, which inside the building would show you the way to get there.
I'm just going to say to you all that actually Andrew has a very huge online presence. There's some very, very cool videos of him talking about other work that he's done. So for instance, how you produce a dancing chair that's looking, it's sort of an anthropomorphic interpretation of that chair, things like that. So if you do go online, you can find some very, very cool and exciting and beautiful other examples of Andrew's work. So if there are no further questions, I would just like to say thank you so much. That was an inspiring and fabulous talk, Andrew. So thank you. And remember, of course, on your way out to hand in your answers to our Blackboard question, and donors to the Institute do make contact with us.